All right, so we're talking about linear functions. So now, okay, this is usually where algebra students have a little bit of a trouble because we just were spending time deciding if something was or wasn't a function, correct? Like, is it a function, is it not a function? So now we're looking at only functions and we're deciding is it linear or nonlinear. Okay, so if we have a tree, right, let's see here. So we've got function, yes or no. So now we're going off here, we're going to have linear or nonlinear. Okay, so no longer are we deciding is it a function or not. Now we're going down this direction and dividing these functions into two categories. Okay, so if we look here, we have some vocabulary. We're going to have linear equation in two variables. So up until this point, we've really only had one variable, right, per equation we're solving. It's either x or y or z or t or r, whatever. Now we've got two variables. This should look familiar to you. Y equals mx plus b. Sound familiar? Is it bringing back some like haunting memories from 7th grade? Y equals mx plus b? Yeah. Y equals mx plus b? Okay, who remembers what the m stands for? It has nothing to do with the letter m, but what does that m stand for? Who said it? Slope is correct. And what does b stand for? What does that letter b stand for in this equation? Y-intercept. You must have had a really good breakfast this morning. Yep.
Yeah, Mr. Klaus.
What did he say?
Mr. Klaus made sure you knew it. If you did, yeah, Mr. Klaus made sure we knew this, but I still don't.
In 6th grade?
Yeah.
Okay, well, that's fine. I mean,
if you didn't know this, you'd be like, why don't you know it?
Okay. Okay. Well, you know what? You all know it, right? Yeah. It worked. I'm going to let them know it worked. Okay. So we've got this linear equation in two variables, so we're going to be focusing a lot on this situation, this y equals mx plus b, over and over and over again. We also need the definition of a linear function because we're going to be identifying them, right? And this is the graph of a non-vertical line. The word linear has the word line in it, so we're looking for straight lines, but it can't be vertical. Who can tell me why that line can't be vertical? Why?
Because they don't all intersect.
You're close, Caitlin. It wouldn't be a function if they all had the same x, right? So a vertical line means every x value is the same on the graph, and so then it's no longer a function, so we can't even decide if it's linear if it's not first a function. Okay, so that's why we have that non-vertical situation there. So then a non-linear function. Did somebody have a question? A nonlinear function does not have a constant rate of change using addition or subtraction. Okay, so that's another key point there is that your rate of change has to be by addition or subtraction. Multiplication, it looks cool, but that's not a constant rate of change, right? You don't have the same thing happening between each ordered pair. Right, so right now this all kind of seems like gibberish, but we're going to start applying it. You'll be like, oh, that's why we needed that vocab. Okay, So what if we're just identifying linear functions from graphs? So let's start that. So we're just going to doodle some graphs here. Some of them are going to be more obvious than others as to why they're considered a nonlinear function. So I have my x and my y-axis, and I have a little squiggle. First of all, is this a function?
Yeah.
Sure is. None of my x values repeat. Is it nonlinear, or is it linear, meaning it's a straight line?
No.
Nope. So this would be a nonlinear function. We know it's a function because none of my x values repeat. Is it linear?
Yes.
Sure is. This third one always confuses people because it's like, maybe it's two straight lines, but is it going to have a constant rate of change if it has like a vertex in the middle of it? No, so it breaks that rule. So this is also a nonlinear function. Even though we've got two straight lines, it breaks the rule. And then this last one